absolute, almost unquestionable certainty about what happens next, and specifically what is pulling you down.
Right, gravity.
Yeah, exactly, gravity. The ultimate invisible tether. I mean, you jump up and the water rushes up to meet you. Or, well, rather, the earth pulls you back down toward the water. It is arguably the most common sense physical experience we have as human beings, you know?
Oh, absolutely. It feels incredibly tangible. Like a literal rope has just been attached to your center of mass and it's just dragging you relentlessly toward the center of the planet. Your senses give you this very clear, very specific narrative about a force acting upon you.
Yeah, you feel the wind rushing past you, your stomach drops into your shoes, and you just know without a shadow of a doubt that this massive invisible hand has grabbed hold of you. It's the defining rule of living on this rock. But, and here is the crux of what we are doing today in this deep dive. The moment you start looking at the actual physics of that fall, and I mean really looking at it through the lens of general relativity and modern quantum theory, that invisible rope completely vanishes.
It really does. The hand just lets go.
Exactly. We are suddenly forced to look at a reality where your basic everyday common sense is, well, it's actively, continuously lying to you.
It is the ultimate cosmic sleight of hand. I mean, the universe is presenting you with an illusion so convincing that it took humanity thousands of years to even begin to question it.
Welcome to this deep dive. Today, our mission is, quite honestly, it's going to bend your mind a little bit, or maybe a lot.
Probably a lot.
Yeah. We are going to completely dismantle your common sense understanding of gravity, and we're going to do it by exploring some of the most fascinating theoretical physics and philosophical debates out there right now.
We have a massive stack of sources today, too.
We really do. We're pulling from the physics lectures of Sabine Hossenfelder, Neil Turok's work on the Big Bang, explorations of dark matter, quantum entanglement, and even those really intense philosophical debates that equate gravity with God. But we aren't just going to list off theories. We are going to build this reality from the ground up.
Starting with the floor beneath your feet, stretching out into the cosmic web, and peering all the way back into the Big Bang itself.
So the central thesis here, to explain simply why gravity is not a pulling force, but rather a space-time effect.
Right, it's a quirk of geometry. And understanding that geometry, well, it unlocks some truly wild concepts.
We're going to see how this invisible architecture shapes galaxies, look into the terrifying nature of the quantum void, and eventually investigate this radical idea that gravity might just be an emergent byproduct of entropy.
I realize that mapping out a journey from a diving board to quantum entropy sounds, incredibly abstract, like the kind of heavy physics that requires a chalkboard full of Greek letters.
Yeah, nobody wants that.
Exactly.
Yeah.
But our goal is to ground every single one of these concepts in reality, because as counterintuitive as these ideas seem, they dictate the fundamental mechanical nature of the room you are sitting in at this exact moment.
Okay, let's unpack this. Let's start right there. In the room you're in. I want you to imagine something for a second. Imagine you take your smartphone, which, has a very sensitive accelerometer built into it to track movement, and you lay it perfectly flat on a table.
Just dead still.
Right, it is dead still. Common sense, the same common sense that tells you gravity pulls you off the diving board, dictates that because the phone is just sitting there, its acceleration is zero.
Because it's not moving.
Exactly. But according to Sabine Hossenfelder's breakdown of Einstein's general relativity in our sources, that common sense assumption is completely mathematically wrong. If you look at the raw data of that accelerometer sitting perfectly still on a flat table, it does not read zero. It reads an upward acceleration of 9.8 meters per second squared.
Yeah, and this is usually the exact moment where the human brain glitches. I mean, the immediate response is always, how can an object that is visibly sitting perfectly still relative to the room around it be accelerating upward?
Let me see if I can translate this into an analogy that strips away the familiar environment of the Earth, because the Earth tricks us. Imagine you have a plain, boring metal spring, the kind you'd find in a mattress.
Got it.
You take this spring out into deep, empty outer space, the deep void light years away from any planets or black holes. You tie one end of this spring to the back of a rocket, and the rocket blasts off, accelerating forward. What happens to the spring?
Well, the physics there are very straightforward. The spring stretches. The acceleration of the rocket creates a force on the mass of the spring. It's just Newton's second law, right? Force equals mass times acceleration.
Right, so you accelerate the rocket, the spring experiences force, and it physically stretches out. The stretch is the physical proof of the force.
Yes.
Now, let's take that exact same spring, bring it all the way back to Earth, and drop it out of a high window, like a dropped ball. As it falls down toward the ground, does it stretch?
It does not.
Yeah.
I mean, if you had a high-speed camera falling alongside it, you would observe that the coils remain perfectly unstretched for the entirety of the fall.
And that right there is the wild part. That is the thread we have to pull. While the spring is falling toward the Earth, accelerating at 9.8 meters per second squared from our perspective, the spring itself is in what physicists call free fall.
Right.
Because the coils aren't stretching, the physical matter of that spring is telling us, objectively, that there is zero force acting upon it. The falling spring experiences absolutely no force. None.
This is the brilliance of Einstein's famous elevator thought experiment.
Okay.
He realized that this lack of force in a fall reveals a really fundamental truth about reality.
Break that down for us.
Imagine you are inside a completely closed box, like a windowless elevator. If you are floating weightless in the center of that box, Einstein posited that there is absolutely no physical experiment you can do inside that box to tell the difference between two very distinct scenarios.
Okay, what are they?
Scenario 1. The box is floating in deep, empty space, far from any gravitational influence. Scenario 2. The box is freely falling down an infinite elevator shaft on Earth. In both scenarios, you float. In both scenarios, you feel no force.
Wow.
Yeah. To the physics of the universe, freely falling in a gravitational field and floating in deep empty space are the exact same state of being.
Okay, I follow that. If I am falling, I feel no force. But wait, I feel weight right now. My body feels heavy pushing into this chair. How is that not a downward gravitational force?
We have to go back to Einstein's windowless elevator. Remember, floating in space and falling on Earth are identical. But what happens if you want to create the sensation of weight in deep space?
You'd fire a rocket.
Exactly. You fire a rocket attached to the bottom of the elevator. If that rocket accelerates the elevator upward at exactly 9.8 meters per second squared, the floor of the elevator will push up against your feet. You will feel heavy.
Oh, I see.
You stand on the floor, and if you drop an apple, the floor will accelerate up to meet it, making it look like the apple fell.
Wait, really? Are you saying that sitting in my chair right now is physically identical to being in a rocket accelerating through space?
That is precisely what the equivalence principle of general relativity states.
Yeah.
The sensation you call gravity pulling you down is, in empirical reality, the floor pushing you up. You are continuously being accelerated upward.
That is incredibly difficult to visualize. I mean, the Earth is a sphere. If the ground is accelerating upward everywhere, the planet would be expanding like a balloon, getting bigger and bigger, which obviously isn't happening.
I mean, it's not expanding.
So how can the ground be accelerating me upward without the planet physically expanding in size?
To understand that, you have to understand what mass does to the space around it. Earth is a massive sphere of matter. And massive objects don't just sit in space. They warp the geometry of space around them. They curve it inward.
Okay, they curve it.
Yeah. If the Earth were made of dust with no internal forces, that curvature of spacetime would cause all that dust to naturally flow inward, condensing smaller and smaller. Without any opposing force, the geometry of spacetime created by the Earth's mass would cause the entire planet to collapse in on itself until it formed a tiny black hole about 3 millimeters in diameter.
A 3-millimeter black hole, that is a deeply terrifying visual. The entire mass of the planet, oceans, mountains, all of it, crushed into a point smaller than a pea.
It's the natural geometric endpoint for that much mass. But obviously, we are not a 3-millimeter black hole.
Right, thankfully.
And why? Because matter has internal pressure. The Earth is made of rock, magma, iron. Those materials are made of atoms, and atoms are bound by electromagnetism and quantum mechanics. The electrons in those atoms violently repel each other. They refuse to be crushed.
So they push back.
Exactly. The entire physical structure of the Earth, from the core to the concrete floor beneath your chair, is pushing outward, fiercely resisting the natural inward curvature of spacetime.
So when I sit here and feel weight, I am not feeling a gravitational pull. I am literally feeling the atomic bonds of the Earth's structure refusing to be crushed into a black hole.
Yes.
The planet's structural integrity is acting like the engine of a rocket, constantly pushing the floor up against me, accelerating me upward against the warped geometry of space.
Exactly. You are constantly accelerating because the ground is continuously obstructing your natural path through space-time, which would be freefall. The feeling of weight is simply the physical trauma of being constantly accelerated.
That completely flips the script. Feeling heavy isn't a state of rest. Feeling heavy is a state of constant, aggressive physical acceleration.
Right. The only time you're truly at rest, experiencing zero force, is when you are falling. It's a radical reimagining of reality. Gravity is not a force that exists upon objects. It is the shape of the universe itself.
Which naturally leads us to the next massive question. If there is no invisible rope pulling things together, how does motion work on a cosmic scale? How do planets orbit the sun?
Well, let's start with an empty, perfectly flat universe with no stars or planets. An object with no forces acting on it just moves in a perfectly straight line forever.
But the universe isn't empty. We have mass. And as you mentioned, mass warps the geometry of space. Now, whenever this is explained in documentaries, they always use the exact same visual, the rubber sheet analogy.
Ah, yes. The rubber sheet.
You take a stretched rubber sheet, drop a heavy bowling ball right in the middle, the weight pulls the sheet down, creating a funnel, and you take a smaller marble representing Earth and roll it across the sheet. The marble's straight path gets caught in the dip and it spirals around the bowling ball. It gives you this intuitive visual of how the sun's mass bends space.
It is a beautiful visual, and it's basically entirely responsible for how the general public visualizes general relativity. But what's fascinating here is there is a massive fundamental flaw with that analogy, a logical trap.
Let's spring the trap. What's the flaw?
Think about the mechanics of the analogy itself. Why does the bowling ball sink into the rubber sheet?
Because it's heavy. Gravity's pulling it down.
Exactly. And why does the marble roll down the slope toward the bowling ball?
Because gravity pulls things down slopes.
Precisely. The analogy uses Earth's literal downward gravity to explain how gravity works in space. It is a completely circular argument. You cannot explain the concept of gravity by invoking gravity as the mechanism of the explanation.
Oh, wow. I've seen that analogy 100 times, and I never realized it was cheating.
It really is. There's no universal down in space for things to sink into.
So how do we visualize it without the rubber sheet? How do we understand orbits without a magical downward pull?
We have to divorce ourselves entirely from physical sheets. We must understand it purely as intrinsic geometry. John Archibald Wheeler summed it up elegantly. Mass tells spacetime how to curve, and spacetime tells mass how to move.
Okay, break that down for me. What is the marble the Earth actually doing?
It is doing exactly what it would do in an empty flat universe. It's moving in a straight line. But the space it is moving through is no longer flat. The sun's mass has created what physicists call a geodesic, the shortest possible path between 2 points in curved space.
So the Earth feels no force.
Right, it feels no force pulling it toward the sun. It is simply traveling in a straight line, completely unbothered. But because the spacetime itself is curved into a loop around the sun, that straight line traces an orbit.
So the Earth thinks it's driving on a perfectly straight highway, but the highway itself has been bent into a circle by the mass of the sun.
Exactly. And this geometric warping shapes the architecture of the entire universe. Over billions of years, matter follows these invisible curves. Dust follows the curves to form stars. Stars follow them to cluster into galaxies. And galaxies follow these massive ancient curves to form the cosmic web.
The cosmic web. Strands of galaxies stretching across billions of light years. And what's truly staggering is we can actually observe and measure this geometry at work. Which brings up a really crucial piece of research from our sources.
You're referring to the Science Alert article about the MACS J1149 cluster.
Yes. Scientists tested Newton's inverse square law of gravity on a massive scale. They looked at a galaxy cluster called MACS J1149.6 plus 2223. This structure is 5 to 7 billion light years away from us.
To put that in perspective, the light we are seeing began its journey before the Earth even existed. Testing the mechanics of gravity across that void is a monumental task.
Right, you can't exactly drop a spring out of a window 5 billion light years away. So how do they measure the movement? The methodology is fascinating. They use the kinematic Sunyaev-Zeldovich effect.
Yes, and that requires looking at the cosmic microwave background, or CMB, the afterglow of the Big Bang itself. It's a bath of ancient microwave photons traveling for over 13 billion years.
Now picture these ancient photons streaming through the void. Occasionally they pass straight through a massive galaxy cluster, and these clusters are surrounded by vast clouds of unbelievably hot gas teeming with highly energetic free electrons. When the ancient CMB photons hit this superheated gas, they scatter off the fast-moving electrons.
And in that collision, the electrons impart a tiny kick of energy to the photons. They shift the frequency of the light ever so slightly.
Exactly. And because scientists know what the baseline frequency of the CMB should be, they can look at how much it shifted. That tiny shift acts like a cosmic speedometer. They can calculate exactly how fast these distant clusters are moving toward one another.
The precision required is staggering, but the results.
Yeah.
It was a massive validation for classical geometric gravity. They found that the gravitational attraction fades with distance, exactly as predicted by the classical theories of Newton and Einstein.
The math holds perfectly firm even across billions of light years.
And the reason this is critical is it strikes a major blow in the debate about dark matter.
Right, because galaxies are spinning so fast that the visible mass shouldn't create enough gravity to hold them together. The prevailing theory is invisible. Dark matter provides the extra mass to curve space. But some physicists hate inventing invisible matter.
So they propose modified gravity, or MOND, the idea that maybe gravity behaves differently over massive distances.
But the MACS J11149 study shuts that door. By measuring the velocities using the CMB photons, they proved gravity does not modify over vast cosmic distances. It weakens following the exact same inverse square law.
Which means if the laws of gravity aren't changing, the only way to explain the movement of these galaxies is that there is, in fact, invisible mass. Dark matter is mathematically required. The invisible architecture demands an invisible architect.
An invisible architecture holding the cosmos together. You know, when you describe the laws of space-time geometry like that, an invisible, omnipresent, universal rule that sustains all of physical order, it sounds suspiciously like how classical theologians describe God.
It is an unavoidable parallel, and it brings us to a fascinating intersection between physics and metaphysics, the God is gravity debate. We're contrasting the purely physical explanation of gravity with its broader theological interpretations.
Let's lay out both sides of this argument impartially. The argument for equating God and gravity, the pro side, is surprisingly robust. Think about the defining attributes of a monotheistic deity: omnipresence, invisibility, sustaining power.
Right.
Advocates point heavily to Scripture, like Colossians 1.17, which explicitly says, "In him all things hold together." That is a perfectly accurate poetic description of space-time geometry.
The historical context is vital too. Isaac Newton, when he formulated his law of gravitation, was actually horrified by his own discovery. He hated the idea of action at a distance through a vacuum.
Because dead matter shouldn't be able to just pull other dead matter across millions of miles of empty space.
Precisely. To Newton, dead matter possessed no agency. Therefore, the invisible, sustaining power that moved the planets had to be the direct, continuous, localized action of God's will.
Wow, so he literally attributed this first mover power to God. And you have other parallels, like Job 26.7 saying the earth is suspended over nothing. Even Occam's razor might suggest that if two concepts share all functional properties, they could be the same.
And Einstein's general relativity even deepens this pro-argument. By redefining gravity away from a mechanical pulling force and establishing it as the fundamental geometry of existence, Einstein created what theologians call an Einsteinian sublime, a structural analogy for divine immanence.
It's a beautiful synthesis. But when we look at the con argument in our sources, the theological pushback is fierce. The primary counterargument is that gravity is fundamentally, inescapably impersonal. It possesses no will.
Exactly. It acts with perfect uniformity on a saint and a murderer alike. They both fall at 9.8 meters per second squared. Gravity cannot forgive. It cannot create matter out of absolute nothingness. And it cannot answer out of a whirlwind.
There is also a severe philosophical barrier here. The philosopher Gilbert Ryle's concept of a category mistake. He used this analogy. Imagine a visitor comes to Oxford. You show them the libraries, dormitories, lecture halls. At the end, they ask, where is the university?
Right, they assume the university is another physical building, rather than the abstract concept that encompasses all the buildings.
And equating God with gravity makes the exact same error. Gravity is just one of the gears in the clock. But in classical theism, God is the clockmaker. Pointing to a gear and saying, that is the clockmaker, misunderstands the category.
And perhaps the most devastating argument against equating the two is the problem of evil. Gravity is indiscriminate in its destruction. It causes catastrophic tsunamis, fatal falls, and black holes that shred solar systems. If gravity is God, God is responsible for indiscriminate destruction.
So what does this all mean for the listener? While physically redundant and theologically dangerous to classical theists, equating the two serves as a beautiful metaphor for mystics and poets to feel a sense of awe.
Awe is the natural human response to the cosmos. But, awe has a sharp flip side. Confronting the unshielded reality of the universe sometimes inspires an isolating, existential terror.
Which brings us perfectly to the experience of William Shatner, the iconic Captain Kirk. At age 90, he actually went to space. The expectation was he'd come back weeping at the majesty of the cosmos. But when he stepped out of the capsule, he was profoundly shaken.
Yeah, he wrote that when he looked out the window, away from Earth, he didn't see a beautiful starry expanse. He saw a cold, dark, suffocating black void.
He described an overwhelming, all-encompassing fear of death. The contrast between the warm blue Earth and the absolute hostile blackness of space hit him with profound grief. This is the human emotional response to the vast, empty nature of our universe.
But this raises an important question. When Shatner looked out into the black void, was he actually looking at nothing?
Well, according to Brian Cox and quantum field theory, absolute nothingness is physically impossible in our universe.
It really is. Imagine a thought experiment. You take a box out in the deepest intergalactic void. You pump out every atom, cool it to absolute zero, extract every photon, shield it from all fields. You have removed everything.
Common sense says you have a box of nothing.
But you don't. The space itself is still there. And in quantum mechanics, space is never empty.
Because space is filled with quantum fields. Physicist David Tong compares these fields to a fluid, or like an invisible heavy molasses that permeates every millimeter of the universe. An electron isn't an isolated object, it's just a localized ripple in the underlying electron field.
And even when a field has no ripples, when it's in its lowest possible vacuum state, it is still active. It possesses zero-point energy. The Heisenberg uncertainty principle dictates a quantum system can never have exactly zero energy.
So the molasses is always boiling, and this boiling produces virtual particles. How do these challenge the idea of absolute nothingness?
Well, because the fields contain this jittering zero-point energy, the vacuum of space is constantly borrowing energy from itself. Spontaneously, pairs of positive and negative particles pop into existence.
They just materialize.
Yes, but they're on borrowed time. Within a microscopic fraction of a second, they attract, collide, and annihilate each other, returning the energy to the field.
So the universe is teeming with virtual particles constantly popping in and out. Because of dark energy and these fields, the universe literally doesn't understand the concept of complete emptiness.
Which presents a massive headache. The origin problem. If the universe isn't empty now, how did it start?
The standard model is cosmic inflation. In a fraction of a second after the universe's birth, an unstable energy field caused space to expand exponentially, like 10 to the 78th power times bigger instantly. It supposedly solved the horizon, flatness, and monopole problems.
But Neil Turok argues that inflation is entirely ad hoc. You just put in a hypothetical inflaton field to get the results you want without making strict falsifiable predictions.
Here's where it gets really interesting. Turok proposes we don't need inflation. He theorizes the Big Bang was a mirror. Using CPT-symmetry charge, parity, time, he theorizes an identical mirror universe expanding backward in time on the other side of the Big Bang singularity.
Right, and the reason this works is it replaces the singularity. Normally, if you rewind the math of general relativity, you hit a point of infinite density. The math breaks.
A dead end.
But Turok's math shows the radiation-dominated early universe is analytic. It's smooth. Instead of a broken wall, the math glides seamlessly through the zero point into the mirror universe.
And this minimal theory requires no new particles. He calculated that you need exactly 36 dimensionless fields to balance the energy, solving the vacuum catastrophe organically.
And it makes a strict prediction. Turok's mirror universe requires a right-handed neutrino to exist to maintain perfect symmetry.
And because it only interacts gravitationally, that right-handed neutrino is the exact source of dark matter. Plus, it predicts the lightest left-handed neutrino must be perfectly massless. If it has mass, his theory is dead.
That's a true testable theory.
It's incredibly elegant. But it forces us to ask, where does gravity fit into the quantum realm? Why do physicists disagree on whether gravity is a fundamental or emergent force?
This brings us to Eric Verlinde's theory of entropic gravity. He proposes gravity might not be fundamental at all. Instead, it might be an emergent entropic byproduct.
Let's use the coiling molecule analogy. Imagine a long polymer molecule in a microscopic box. Because of thermal energy, it jiggles. Over time, it naturally coils up into a messy clump. Why? Because of entropy.
Right. There are vastly more ways to be coiled, which is high entropy, than perfectly straight, which is low entropy.
So it moves toward disorder. If you grab the ends and pull them apart, it resists you. It feels like an elastic band pulling back. but there's no coiling force. This tendency toward disorder creates an entropic force.
And Verlind argues gravity acts the exact same way. But to understand this, we need the holographic principle. Juan Maldesena's adds S as CFT correspondence and John Archibald Wheeler's it from bit.
So it from bit means the universe is fundamentally made of pure yes-no quantum information. And the holographic principle suggests the entire 3D volume of our universe is actually a holographic projection encoded on a 2D quantum boundary.
Exactly. On this 2D boundary, quantum information is constantly vibrating, entangling, and trying to maximize its entropy. When a physical object, like a particle, falls toward a mass in our 3D world, what's actually happening on the 2D boundary?
The information is just shifting into a messier, vastly more statistically probable state of entangled information.
Yes, the universe is acting like the coiling molecule. We experience that statistical data shuffle as physical objects falling toward each other. Gravity is just the statistical side effect of the universe maximizing entropy on that boundary.
So viewing gravity as an emergent attractive force changes our entire quantum understanding. It bridges the impossible gap between quantum mechanics and general relativity by suggesting space and gravity aren't fundamental stages. They are illusions generated by quantum entanglement networks.
You cannot quantize gravity because gravity is just the macro-scale shadow cast by quantum information.
It's absolutely breathtaking. We've gone from feeling weight on Earth, which is actually just the floor accelerating us upward, to the geometry of the cosmic web, to the awe of a theological sustainer, to the boiling reality of the quantum void.
And then to Turok's mirror universe, and finally this shattering idea that gravity is just an entropic illusion.
Which leaves me with a final provocative thought. If gravity isn't a force, but rather the emergent result of quantum information entangling and processing on the boundary of our universe, then perhaps the reason we struggle to unify physics is that we are looking at the hardware of reality, when gravity is actually just the software keeping the simulation running.
Oh, wow.
Are we just the universe's way of observing its own code? It's something to think about the next time you jump off a diving board, waiting for the universe's code to execute. Thank you for joining us on this deep dive. Keep questioning the reality around you.